as the title shows, there is a range of topics which are connected to meteors here, ionosphere, optical observations, infrasound, and seismic data. And the list of authors also shows that it's a wide range of topics that it is only partly covered by this presentation. So actually, we are working on these topics under the so-called GNOP project, which aims to analyze near-Earth hazards from meteoritic bodies. So it covers a lot of topics: telescopic analysis of asteroids, meteor research, lunar impact flash monitoring, meteorite analysis, and impact crater analysis. Actually, I discussed this last one last year in Bolmansruch in the last IMC. And now here I'm going to talk about two specific topics with interesting examples. The first is about the ionospheric observations. So here is a short slide on the methods. There is a so-called sporadic E layer in the ionosphere in this elevation around 100 and 150 kilometer, where you can have enhanced electron density, which comes from meteors, and these are vertically thin regions produced by wind shear. It can be observed that this layer, this sporadic E layer, is enhanced during meteor observations. It turned out in the last few years. But it's quite difficult to quantify how does this ionospheric E layer occurrence depend on meteor activity. Sorry. So here this ion sound was used, can be seen on the right for the observations. The other small topic which I discussed is the infrasound observation. We have an array in the Matra Mountains. This is the name which analyzes the detector, which records actually atmospheric pressure change. So it is a microbarometer with digitalizing the changes, and using this 250-meter diameter with various direction arms on it, it is able to record the arrival direction of the atmospheric blast wave. And there are seismometers, of course, in Hungary with many stations, which were also included in the observations. So I'm presenting some examples. They're not much, but several examples we have where there were successful observations. First, about the ionospheric observation. There was a Leonid campaign in last year. You can see 2019 November, where high-resolution ionograms were recorded, which required high-frequency sampling, higher than usually it was used. So it was searching for faint, short-lived sporadic E layers. And in 3 cases, it was possible to link the appearance of this E layer with meteor observations. Here you can see one example where there was a +1 magnitude meteor. Here you can see on the left. Unfortunately, it was during full moon. This is the right side large blob, the full moon. It was a relatively high meteor, almost close to the zenith, 85 degrees above the horizon. And here on the right, you can see these so-called ionograms, which show the frequency and the height in the 2 axes. And the red arrow marks the meteor phenomena of this meteor. So it was possible to record 3 cases, this short appearance of sporadic E layer in the same time when the camera was recorded moderately bright or middle bright meteor. The other topic what I would like to present is the linkage of infrasound observation to optical observation. Here 2 examples can be seen. The infrasound map or infrasound curve at the bottom, I mean in the middle of the diagram with green color can be seen. And this infrasound effect was linked to these meteors at the bottom, these bolides from also last autumn. Here you can see the specific data of these meteors. And the most interesting, when the seismic observation came into view, was the famous bright fireball in this February. You know about it. It was a roughly 1.5 meter diameter meteoroid about Croatia and the Slovenia region. Was exploded relatively low, 34 kilometer high, near to Zagreb, and it released this amount of energy, 0.3 kiloton TNT. Sorry, it's a typo error. It should be TNT by the explosion. And it produced seismological signal. How can it happen? Probably the atmospheric blast that was caused by the meteor, the explosion, reached the ground and shook the surface. The surface was shaken by this atmospheric effect. You can see one example of this seismic effect in Hungary, about 160 kilometers from the explosion, at this so-called Becehely observing station. If we put all of the seismograms recorded the meteor explosion and the atmospheric blast consequences on the surface, we can have this diagram on the right, where the different seismological curves, seismograms, are indicated from the left toward the right according to the growing distance from the epicenter of the event. So there was a disturbance in the atmosphere sweeping across the stations. It was recorded most of the stations, and if we calculate the arrival time, it turns out, yes, it is what it should be, about 300 meters per second, close to the speed of sound. So we have a bolide, an air blast, and the air blast produced ground shaking, and that's why we recorded seismic signal. Actually, it was strong enough by this bolide to record this from several 100-kilometer distance. Yes, here you can see actually another way, the same observation. According to the growing distance, the time was also grown as the sound traveled. So many stations observed, most stations observed, some did not observe, which was very too deep in the subsurface. And there can be multiple reflections in the atmosphere. However, it was a clearly different signal from other seismic signals, so from earthquakes. It could be separated. So about the conclusion, if we're using rapid ionosphere measurements, then we can identify individual meteors, which is quite new. There were very few or almost no earlier recording of successful simultaneous observation of one individual meteor and related ionospheric effects. So there is good perspective in this topic. We know there is a dependence of sporadic E-layer characteristics related to meteors, but we have a serious knowledge gap how to link optical and ionospheric effects. We expect there is meteoritic input to the ionosphere with metal ions, which can play a role in the state of the atmosphere. And even in the future, it might be linked to meteor spectroscopy somehow. And there is an idea which has not been tested yet. Most fragile meteoritic particles, these so-called IDPs, ablate too high in the atmosphere to cause observable effect in the optical region. But in theory, it is not impossible that based on ionospheric effects, it might be observable. Regarding infrasound and seismological observations, we might have in the future possibility to analyze some internal properties of meteoroids by these regarding the ablation height or the multiplicity of explosion? Yes. And finally, if we put on a table all of the meteor observing methods like optical, radar, ionospheric, spectra, infrasound, where are the possibilities where we need to explore these ionospheric and infrasound topics? For example, the threshold size of the meteorites, and the possibility how the ablated material does affect the ionosphere. And in theory, there is some possibility to identify some structural aspects regarding the number or duration of explosion in the future. Okay, that's all. Thank you for your attention.
Thank you. I will switch back my sound without echoes. Thank you. I look at the participants. Anyone with raised hand? Not yet. Any question, comment? Suresh. Yep, go ahead.
Yeah, the idea of including with seismic is what we also tried in March, but we didn't get any signals. So that is what I wanted to comment. So I really like the presentation. Thank you so much.
Good. Okay. And have you published it, or do you intend to publish? Okay.
Circo.
Akash, these coincidences that you have observed between meteors and the sporadic E layer, can you really rule out that these are not by chance alignments? I mean, I don't know how many sporadic E events you have, how many meteors, but obviously there may be some, chance coincidence. Could you rule that out?
It was reviewed, it was evaluated, and seemed to be, it's quite probable that it was not a by chance coincidence. I don't know by heart, but so certain duration of time was surveyed, and comparing the ionospheric characteristics with the possible appearance of meteors, and this coincidence seemed to be probably related to real effect. But yes, it's quite important. Actually, this ionospheric observation can record probably only those meteors which happen high above the observer. So it is not able to observe meteors close to the horizon, probably.
All right.
Okay, thank you.
Anyone with further question or comment? Tamo? Yep.
Yep. A small comment in the schema with the comparison of all the observation possibilities. You mentioned it for radio, it's impossible, or it's the localization accuracy is very low.
Yeah.
But it depends a bit. You can with an interferometer, you can get quite high localization accuracy, I think.
Yes, I have to say I'm sorry. My radio meteor knowledge is quite poor. I mean, it's related to about 1 or 2 decades ago knowledge. So sorry, I simply put it low, but you might be probably right. I have to look up the literature, yes, to see about the current localization accuracies. Yes, thank you. It's important note.
Okay, but very, very interesting presentation. Thank you very much.
Thank you.